it's Aashi, an AI and self-driving cars enthusiast. I'm going to be sharing with you my latest project, facial expression recognition. So for the past few weeks, I've been looking into building my own AI, and I found this really cool facial expression recognition tutorial, link in the description, and I decided to follow it.
So I coded it, wrote an article about it,
and here I am. My facial recognition algorithm categorizes each face based on the emotion shown in the image in these 7 categories, with 96% accuracy. But what I was really stuck on was, how does it work? And how does a computer just do that? Turns out it uses something called a convolutional neural network. First, it trains itself to understand facial expressions from a set of label data, and then, using the knowledge from what it's learned, it classifies images of unlabeled data sets. So this is called a train versus test split, and my training data consists of 28,709 images, and the test set consists of 3,809 images. To do this, it must have some kind of existing data, right? So I used the data set of FER 2013, and FER 2013 consists of 48 by 48 grayscale images of faces from the internet.
You can think of a neural network like a human brain. Let's take this picture of Andrew Garfield here. Maybe the first thing you notice is his eyes, which are a little bit smaller, or his nose, which is protruding upwards, or his lips that are facing up like a parabola. And after finding these facial features, you can come to the conclusion that he's probably smiling or his emotion is happiness.
Like we use our brain to find these facial features, our neural network uses layers and it uses filters to find patterns between these facial features. So the first layer will be responsible for finding features like edges, lines, or corners, really basic things. Then I'll move on to more complicated things after figuring out edges, lines, and corners, to eyes, nose, eyebrows, and then finally onto our facial expression classification.
To actually understand how this is applied to facial expression recognition, I've used the example of a handwritten digit 6. So we can divide this up into 3 parts: a diagonal line, vertical line, and a loopy circle pattern. And as you can see, this loopy circle is made up of curves and edges, and that's how it could congregate them together and be able to tell that it's a loopy circle pattern. So similarly, in our convolutional neural network, it will use 3 different filters, and filters are essentially just feature detectors. So we have our diagonal line, vertical line, and loopy circle filter. Also, for the computer to actually understand what I'm putting in, I've put it in -1s and 1s, the values, because that just represents if there's a black or white. So now that I've determined what the computer needs to look for, the diagonal line, the vertical line, and the loopy circle pattern, how exactly does it know where these things are? Well, here it uses something called a convolutional operation. So here I have my original image. The ones just represent where the 6 is. And let's say I just want to look for a loopy circle. And so here I have just my loopy circle if we refer it back here. And what it's going to do is use a 3x3 grid, which scans the image using 1x1 strides. And it's going to multiply this by the convolutional operation. So we take this number over here, -1, multiply it by these individual ones, find the average, and we get a final number over here. This congregates into something called a feature map. Now the benefit of this is that once we start applying more 3x3 filters over our entire thing, eventually we'll find something that looks like this, and doing the math, it brings us to a value that is 1 or at least close to 1. So now that we know anywhere on the feature map, after doing the math, it has a 1 or a number close to 1, we know that that's where the curves or loopy circle pattern is. Now, coming back to our example of facial expression recognition, this loopy circle pattern can be thought of as the eyes or the nostrils because that's kind of like a similar shape. So in the case of facial expression recognition, we can apply this convolutional operation and use things like an eye detector, an eyebrow detector, or lip detector. And it doesn't matter where these eyes are, it will still be able to find where it is. So now that we know where the eyes, the mouth, or the nose are, how exactly do we say that maybe the eyes are a little smaller, or the nose is protruding upwards, the eyebrows are a little bit more scrunched up, and therefore someone is happy or angry? So here, let's take this example of a man. And here we want to detect the eyebrows, so we'll use an edge feature. If we want to detect the nose, then we'll use a line feature. And similarly for the teeth, if we want to detect that, we'll use edge features again. And going on from feature to feature, the ratio between these detected features is used in the emotion detection. So let's say if there's a higher ratio between a circle feature for someone's eyes, they must be a little bigger. Or if a person has edge features for the lips and they have a greater difference, that must mean that their mouth is open. And similarly, for the emotion detection, these small differences between their eyes, where their nose and their lips are, can tell if they're happy, sad, angry, etc.
So that was pretty high level, but there are a couple of layers that make this process much easier.
So one of the things that makes it easier is an activation function, or what I used was ReLU, rectified linear unit. And it's something that allows our model to learn faster and perform better because it makes it nonlinear by actually changing all these negative values from our feature map to 0. Another thing I can use is max pooling, which essentially ensures that the CNN can still classify the image even if it's distorted, rotated, the background is changed, etc. So upon obtaining our feature map, a spatial window of 2 by 2 pixels is defined, like we did with the filters, and the largest value is captured from the feature map of these 4 numbers. So here it would be 1. For the next spatial window, again, it would be 1. And this actually gets rid of 3 out of 4 pixels. This leads to faster processing of the model, speeds up computation, and removes noise in the data. Another layer we can use is the flatten layer. So our model's not 100% going to know if the emotion is angry. There could be other possibilities as well, but using the flatten layer, we're going to tell it to pick its best guess and make its prediction on the most likely option. It also flattens the output of the CNN to produce a single long vector as shown here. Another really basic layer is the dense layer, which feeds all the outputs from the previous layer to all its neurons, and each neuron provides one output to the next layer. So altogether, our neural network receives its input image. We go over it using our filters to identify patterns. We make it go through convolutional, ReLU, and pooling layers multiple times. Uses the flattening layer for classification and a fully connected one. And towards the end, we receive a final number that translates into one of the facial expressions.
And that's how it works. So, of course, towards the end of the neural network, you can't tell 100% that this kid is happy. It'll have a lot of different possibilities, but we're going to tell it to pick its best guess. And that's why my model is 96% accurate. Overall, if you like this video, please like and subscribe.